What you are about to see, no one has ever known. This is the one thing science kept quiet until now. We didn't guess. We dug through years of data to bring you the truth. You have seen it every single day of your life. It has never once been out of reach, never behind a locked door, never hidden across some unimaginable distance. And yet, until shockingly recently, we understood almost nothing real about what it actually is. Every second, it converts 4 million tons of its own mass directly into pure, radiant energy. Light leaving its center right now will not reach its own surface for another 100,000 years. And deep inside it, for decades, physicists kept finding a very specific number that was simply, stubbornly wrong. A mystery that took 40 years and a detector buried a mile underground to finally solve. This is the sun, an ordinary star anchoring everything you have known, and it turns out we barely knew it at all. Start with the basics, because even the basics are strange once you sit with them. The sun holds 99.8% of all the mass in our entire solar system. Everything else, every planet, moon, asteroid, and comet combined, is little more than rounding error orbiting around it. It is built almost entirely from the two simplest elements in the universe, roughly 73% hydrogen and 25% helium by mass, with every heavier element on the periodic table making up the remaining sliver. It is not solid. It is not liquid in any way we would recognize. It is a sphere of plasma, superheated gas stripped of its electrons, held together and shaped entirely by its own gravity, spinning at different speeds depending on latitude, a phenomenon called differential rotation, where the equator completes a rotation in about 25 days while the poles take closer to 35. Working out what the sun was even made of took over a century of careful detective work, conducted entirely from 93 million miles away. In the early 1800s, German optician Joseph von Fraunhofer noticed hundreds of thin, dark lines cutting across the sun's rainbow spectrum when sunlight was passed through a prism, lines that seemed to appear at oddly specific, unchanging positions. Decades later, physicists Gustav Kirchhoff and Robert Bunsen realized these lines were fingerprints, each element absorbing light at its own precise wavelength, meaning the pattern of dark lines in sunlight could reveal exactly which elements existed in the sun's outer layers, without ever needing to physically touch the object being studied. In 1868, astronomers Pierre Janssen and Norman Lockyer, working independently, spotted an unfamiliar line in the sun's spectrum during a solar eclipse that matched no known element on Earth at the time. Lockyer proposed it belonged to a brand new element entirely, naming it helium after Helios, the Greek personification of the sun, a full 27 years before helium was finally isolated and confirmed here on Earth in 1895. It remains, to this day, the only element in the entire periodic table discovered somewhere else in the universe before it was ever found or isolated here on our own planet. At the very center sits the core, and the numbers there stop feeling real almost immediately. Pressure at the sun's core reaches roughly 250 billion times the atmospheric pressure at Earth's surface. Temperature climbs to about 27 million degrees Fahrenheit, 15 million degrees Celsius, hot enough and dense enough to force hydrogen nuclei to overcome their natural repulsion and fuse together into helium, a process called nuclear fusion, releasing the energy that powers essentially everything alive on Earth. Nobody actually knew this was happening until surprisingly late. Throughout the 1800s, physicists including Lord Kelvin seriously proposed that the sun was simply burning like an enormous fire, or slowly shrinking under its own gravity and releasing energy that way, and either explanation implied the sun could only be a few tens of millions of years old at most, a figure that quietly conflicted with mounting geological evidence that the Earth itself was far older than that. It took until 1920 for British astrophysicist Arthur Eddington to first propose, largely from theoretical reasoning about mass and energy inspired by Einstein's then recent work, that the sun might be powered by the fusion of hydrogen into helium deep within its core, converting a tiny fraction of mass directly into a tremendous amount of usable energy. Eddington's idea was met with considerable skepticism at the time, since most physicists did not yet believe stellar cores could plausibly chill for more than about 20 minutes at a time. That visible surface, called the photosphere, sits at a temperature of roughly 10,000 degrees Fahrenheit, and for a long time, common sense suggested that anything above it should simply get cooler the farther out you go, the same way air gets colder the higher you climb above a fire. Instead, astronomers found the exact opposite, and it remains one of the most stubborn open puzzles in solar physics. The sun's outer atmosphere, called the corona, visible to the naked eye only during a total solar eclipse as a pale, ghostly halo stretching far beyond the disk of the sun itself, reaches temperatures of 1 to 3 million degrees Fahrenheit, hundreds of times hotter than the surface directly beneath it. Nobody fully agrees on why. Leading theories point to magnetic reconnection, sudden snapping and realignment of the sun's tangled magnetic field lines releasing enormous bursts of energy directly into the corona, or to a phenomenon called nanoflares, countless tiny, almost imperceptible explosions happening constantly across the sun's surface, individually too small to notice but collectively powerful enough to superheat the entire outer atmosphere. Solving this coronal heating problem, as it is formally known, has occupied solar physicists for the better part of a century, and it is still not considered fully closed. The corona does something else strange, too. It does not just sit there, glowing. It flows outward, constantly, in every direction, as a continuous stream of charged particles called the solar wind. American physicist Eugene Parker first proposed the existence of this outward flow in 1958, and his prediction was met with real skepticism at the time, since nothing in the accepted physics of the day seemed to require the sun's atmosphere to be escaping into space at all. Parker turned out to be correct, and the solar wind he predicted has since been measured streaming outward at speeds between roughly 250 and 500 miles per second, carrying the sun's magnetic field with it and shaping an enormous bubble of influence called the heliosphere that extends far beyond the orbit of Pluto, the boundary at which the solar wind finally weakens enough for interstellar space to take over. In 2018, NASA launched a spacecraft named the Parker Solar Probe in his honor, the first spacecraft ever built specifically to fly directly into the sun's corona rather than simply observe it from a safe distance. Protected by a specially engineered carbon composite heat shield roughly 4.5 inches thick, capable of withstanding temperatures exceeding 2,500 degrees Fahrenheit on its sun-facing side while keeping its instruments on the shadowed side at a comfortable room temperature, the probe has repeatedly dived closer to the sun than any human-made object in history, using repeated gravity-assist flybys of Venus to gradually tighten its orbit closer and closer with each pass. In December 2021, it became the first spacecraft to officially fly through the corona itself, physically touching the sun's outer atmosphere and sampling its particles and magnetic fields directly, closing a gap between prediction and confirmed measurement that had stood since Parker's original 1958 paper. A companion mission, the European Space Agency's Solar Orbiter, launched in 2020, took a different approach entirely, tilting its orbit out of the flat plane most planets and spacecraft travel in specifically to photograph the sun's poles directly for the first time in history, regions that remain permanently out of view from Earth and from every previous solar mission that stayed within the ecliptic plane. Astronomers have also found a way to study the sun's invisible interior without ever sending a spacecraft near it at all, by listening to it instead. The sun's turbulent convective zone constantly generates sound waves, vibrations that ripple through the plasma and cause the entire visible surface to oscillate, rising and falling by small amounts across regions thousands of miles wide, in patterns that repeat every few minutes. A field called helioseismology, developed from the 1960s onward and refined dramatically once space-based observatories could monitor the sun continuously, studies these surface oscillations the same way seismologists study earthquakes on Earth, using the speed and pattern of these internal sound waves to reconstruct temperature, density, and rotation at every depth inside the sun, effectively producing a three-dimensional map of the solar interior without any instrument ever having to physically go there. It was helioseismology that first confirmed the boundary between the radiative zone and the convective zone with real precision, and it continues to reveal subtle details about the solar dynamo that no other method can access. Deep beneath all of this activity, another mystery had been quietly building for decades, one that had nothing to do with heat or wind, and everything to do with a particle so elusive it can pass directly through the entire Earth without ever colliding with a single atom. Nuclear fusion in the sun's core produces not just light, but also enormous numbers of subatomic particles called neutrinos, streaming outward at nearly the speed of light and reaching Earth just minutes after being created, unlike the photons trapped for tens of thousands of years in the radiative zone. Starting in the late 1960s, physicist Raymond Davis Jr. built a detector deep inside a South Dakota gold mine specifically to count these solar neutrinos as they arrived, and the results, refined over decades of careful measurement, kept coming back wrong. The detector consistently found only about 1/3 of the neutrinos that solar physics models predicted the sun should be producing. For 30 years, this discrepancy, known as the solar neutrino problem, left physicists genuinely uncertain whether something was fundamentally wrong with our understanding of how the sun generates energy, or whether something was wrong with our understanding of neutrinos themselves. The answer, when it finally arrived in 2001, turned out to be almost more interesting than either possibility. The Sudbury Neutrino Observatory, built more than a mile underground inside an active nickel mine in Ontario, Canada, specifically to detect all 3 known types or flavors of neutrinos rather than just the one type Davis's original detector could see, confirmed that the sun really was producing exactly the number of neutrinos the models predicted all along. The neutrinos simply were not staying the same type during their 8-minute journey to Earth. They were oscillating, physically changing from one flavor into another mid-flight, a genuinely strange quantum behavior that earlier detectors, tuned to see only a single flavor, had been mostly blind to. The discovery, confirming that neutrinos possess mass at all, something the long-standing standard model of particle physics had originally assumed was impossible, earned Raymond Davis Jr. and physicist Masatoshi Koshiba a share of the 2002 Nobel Prize in Physics, and the Sudbury team's principal investigator, Arthur MacDonald, a share of the 2015 Nobel Prize once oscillation itself was fully confirmed. In other words, the sun had been telling us the truth the entire time. We simply had not yet built an instrument capable of listening correctly. The sun's surface carries its own visible record of an 11-year cycle that has puzzled and fascinated observers for centuries. Sunspots, darker, cooler patches on the photosphere caused by concentrated bundles of magnetic field lines suppressing the convective flow of heat beneath them, rise and fall in number on a roughly 11-year rhythm, first systematically tracked by German astronomer Samuel Heinrich Schwabe in the 1840s. At solar maximum, the sun's surface can be scattered with dozens of active sunspot groups, along with dramatically increased solar flares and coronal mass ejections, enormous eruptions of plasma and magnetic field hurled outward into space. At solar minimum, the surface can go weeks with barely a single visible spot. The most extreme solar storm ever recorded on Earth struck in September 1859, an event now known as the Carrington event after British astronomer Richard Carrington, who witnessed the triggering solar flare directly through his telescope. The resulting geomagnetic storm was powerful enough to induce electrical currents in telegraph wires across Europe and North America. Some operators reportedly able to send messages with their batteries completely disconnected, powered instead by the storm itself, while auroras, normally confined to polar regions, were reported as far south as the Caribbean. A storm of comparable strength striking today, with modern society entirely dependent on satellites, GPS networks, and power grids, could cause disruption on a scale that scientists and engineers have spent years quietly trying to model and prepare for, running scenarios that estimate potential costs reaching into the hundreds of billions of dollars if such an event caught the modern world unprepared. Underneath all of this activity lies the engine that generates the sun's magnetic field in the first place, a process called the solar dynamo, driven by the churning motion of electrically charged plasma deep within the convective zone combined with the sun's differential rotation. That magnetic field does something no planet's magnetic field does. Roughly every 11 years, in step with the sunspot cycle, the sun's entire magnetic field flips, north becoming south and south becoming north, a complete polarity reversal that solar physicists have tracked reliably since the early 20th century. Even though the underlying mechanism driving the exact timing of each flip is still an active area of research, refined further with each new solar cycle observed by modern spacecraft like the Solar Dynamics Observatory, which has watched the sun continuously since 2010, and the earlier Solar and Heliospheric Observatory, still operating decades after its 1995 launch. None of this activity will continue forever, though the timescale involved is almost impossible to hold in the mind meaningfully. The sun is roughly 4.6 billion years into what astronomers estimate is a stable, hydrogen-burning lifetime of about 10 billion years, meaning it currently sits close to the midpoint of its total existence. In roughly 5 billion years, once the hydrogen fuel in its core is finally exhausted, the sun will begin fusing helium instead, swelling dramatically into a red giant, its outer layers expanding possibly far enough to engulf Mercury and Venus entirely, and quite possibly Earth's orbit as well, before eventually shedding its outer layers into space and collapsing down into a dense, slowly cooling stellar remnant called a white dwarf, roughly the size of Earth but containing a significant fraction of the sun's original mass, destined to fade, quietly and without further fusion, essentially forever. There is something worth sitting with in the fact that the object responsible for every living thing on this planet, the single most familiar sight in our entire sky, remained genuinely mysterious in fundamental ways well into the era of spacecraft and particle physics. We had photographed galaxies billions of light years away before we fully understood why the sun's own atmosphere burns hotter than its surface. We had landed instruments on Mars before a mile-deep detector in a Canadian mine finally explained where a third of the sun's expected neutrinos had been hiding the entire time. Familiarity, it turns out, was never the same thing as understanding, no matter how many mornings we watched it rise without a second thought. So, the next clear day you get, and only ever through certified solar filters or eclipse glasses, never with the naked eye, take a genuine moment to actually consider what you are looking at. Not simply a bright disk hanging in a blue sky, but a churning ball of plasma fusing 600 million tons of hydrogen into helium every single second, carrying light that began its journey inside that core tens of thousands of years before you were born, wrapped in an atmosphere hundreds of times hotter than its own surface for reasons we are still working out, flinging invisible particles toward you that reveal secrets about the fundamental nature of matter itself. It has been sitting there in plain sight for your entire life. And in a very real sense, we have only just started learning how to truly see it.